Okay. Good evening, everybody. I am N.S. Venkatraman, Director of Nandini Consultant Center, Chennai. I have pleasure in extending a hearty welcome to every one of you who have responded to our invitation. Semiconductor industry across the world is now undergoing a strain. The strain has occurred mainly due to the short supply of chips, and with the production of the chips or the supply of chips not meeting the demand. This has created some sort of a crisis in the semiconductor industry across the world. Several automobile manufacturers have been forced to curtail the production due to want of chips. Mobile phone producers, electronic parts manufacturers like laptop, computer, television have all curtailed production. So many people are wondering what has happened. And there is some sort of a serious debate going across the world as to what has caused the chip shortage. Is it due to geopolitical factors or due to the impact of the COVID 19 spread across the world, or due to shortage of raw material supply? The final word has not been said about this. To add to the confusion, one of the principal producers of chips in the world, namely Intel, has said that the chip shortage is likely to continue for the next few more years. This has caused some sort of alarm amongst the semiconductor consumers across the world who think that they may have to rework out their plans for the future. In such circumstances, we can't but wonder where India stands. There are tiny countries like Taiwan, South Korea, who all have a big presence in the international semiconductor map. India has much to talk about this. This is a very unfortunate scenario. The government of India is very seriously concerned about this and is very keen to encourage the semiconductor industry in India. It has announced separate incentive programs. Some proactive policy initiatives have been announced, and hopefully, government of India thinks that they can make a significant progress in semiconductor industry in the coming years. In such circumstances, the topic that we have chosen today, namely the status of semiconductor industry across the world and opportunity for Indian industry, has become highly topical. We have Dr. Nandini Venkatraman here, who is an expert in semiconductor, who is going to talk on this subject. Before inviting Dr. Nandini Venkatraman, I invite Mr. Swaminathan Venkatraman of Singapore to give an introductory remark. Mr. Swaminathan Venkatraman is a chemical engineer and MBA from Indian Institute of Management, Ahmedabad. He has worked for over a decade in Europe and Singapore in functions related to supply chain management and related functions, and he is now the director of Nandini Consulting in Singapore, mainly focusing on the international forecasting of various indices, business strategic plans, etc. I invite Mr. Swaminathan Venkatraman to give his introductory talk. Over to Mr. Swaminathan Venkatraman.
Thank you, Mr. Venkatraman. It's a pleasure to give introductory remarks before Dr. Nandini Venkatraman can start her talk. Welcome to today's topic of discussion, which is developments in semiconductor industry, opportunities for India. We are now in a digital age and we are consuming electronics at an unprecedented scale. Last year, it said that the worldwide shipment of electronic devices such as PCs, tablets, and mobile phones totaled almost 2.2 billion units. Semiconductors or chipsets are used in all modern electronic devices and technologies with a range of applications from consumer electronic products, IT hardware, defense technology, industrial electronics, medical electronics, industrial automation devices, and so on. So basically, wherever there are computational devices, you have a semiconductor chipset somewhere driving behind it. There are also newer and newer application areas that are coming up, like Internet of Things, which is basically connected devices, autonomous driving, which is likely to shape the car industry and in the future, cloud computing, AI, which are all driving the next leg of growth for higher and more advanced chipsets. So it is clear that economies that have a large production of these chips have benefited the most in the past and will also benefit enormously in economic terms in future. And more importantly, they will get to control vital parts of global economy because every device is likely to be controlled by some sort of a chipset inside it. There are only a few countries in the world which are large product producers of semiconductor chips today, such as US, Taiwan, Japan, Korea, and China, and they have a very strong stranglehold on the global semiconductor industry. See, amidst this rising demand for electronics, today India is a very large net importer of semiconductor chips. Total electronic imports of India last year alone was almost $50 billion. This is in comparison, for example, with our oil imports of about $100 billion. So, and the growth rate of import of semiconductor products exceeds the growth in oil imports in the last few years. So, we are very heavily becoming dependent on import of electronic products, and which are very critical to our self-sufficiency. India has made attempts in the past to set up domestic manufacturing unit for semiconductors. We made a first attempt somewhere in 2006 when a Bangalore-based company called SEM India signed an MOU with Andhra Pradesh government to set up a wafer manufacturing SEZ, for which it was allotted about 1,200 acres of land. It was a $3 billion project, but it could not take off. At the same time, the government of India was trying to woo Intel to set up a semiconductor facility in India. Intel evaluated whether it wanted to set it up in India or China, and ultimately it chose China, which is a very big setback for India, and China has benefited enormously from that. In 2011, government came up with a maiden national electronic policy, and it invited proposals for setting up fab units in India. It received about 24 expressions of interest, and by 2014, two of them were given the nod. But both could not take off due to a number of reasons, including inability to tie up funding, unviable business case, infrastructure, and so on. After that, we have not succeeded in making much development, although there has been considerable discussion in government circles that we need to move fast in this in this field. So where does this leave India now in the context of global development? Now, this is what we are going to listen to in the next hour or so from our speaker, Dr. Nandini Venkatraman. Dr. Nandini Venkatraman is a semiconductor engineer with a PhD in material science and engineering from University of Arizona. She has worked in functions related to process technology development in memory fabs at Intel Corporation in the United States and Micron Semiconductor in Singapore. She has authored or co-authored about 15 technical papers in international peer-reviewed journals and conference proceedings, in addition to co-authoring a chapter in the Handbook of Semiconductor Cleaning. So let's listen to Dr. Nandini Venkatraman, and listen to her talk on developments in semiconductor industry and opportunities for India. Over to Dr. Nandini.
Thank you for the generous introduction, Mr. Venkatraman and Mr. Swaminathan. Mr. Swaminathan has very succinctly summarized some of the key aspects of the semiconductor industry as it stands today. So in the next 50 minutes or so, I will attempt to provide a perspective of the global semiconductor manufacturing industry. I will try to contextualize it to India's current and future needs and the opportunities and challenges for India in semiconductor manufacturing. I will now share a slide deck to help guide the talk. Swami, can you confirm that you're seeing the slide?
Yeah, we are able to. Yes.
Okay. So the outline of my talk will be as follows. So I will introduce the key aspects of the semiconductor business. I will talk about how the global semiconductor industry today is organized structurally. I will talk about some of the key recent developments that are shaping the semiconductor industry. And then I will go on to the future trends and growth drivers for this industry. And finally, I will talk about some of the opportunities and challenges in front of India and how it needs to proceed in the semiconductor manufacturing space. So according to data from the World Semiconductor Trade Statistics, which is one of the premier organizations that publishes trade data on a monthly basis, The global semiconductor industry revenue in 2020 was around 440 billion US dollars. And the industry on average has been growing at a rate of 6 to 6.5% year on year over the last couple of decades. As for the Indian scenario, India's contribution to the global semiconductor industry has been mostly around chip design. We have substantial competence in chip design. Does not really have a manufacturing capability, does not really make and sell products per se. But if you think about the revenue for India, so the semiconductor R&D revenue itself has been estimated to be about $2.5 billion, according to the Indian Electronics and Semiconductor Association. Under the overall bracket of semiconductors, the key product segments in the semiconductor industry can be broadly classified as discrete components, as optoelectronics and sensors, and integrated circuits. Integrated circuits are what is most commonly referred to in business press as chips. They account for nearly 80% of the market. So integrated circuits are basically electronic circuits. They have billions of circuit elements, mostly transistors, which are interconnected in various circuit configurations, and they are fabricated on a single piece of semiconductor substrate. Now, the vast majority of the integrated circuits that are produced today, they are manufactured on silicon substrates. But there are also ICs that are manufactured on compound semiconductor materials, such as gallium arsenide, silicon carbide, and so on, particularly for high power applications, such as in electric vehicles. Now, integrated circuits itself, in turn, it can be very broadly classified according to its functionality. So we normally talk about digital and analog ICs. So under the bracket of digital ICs, you have what is called logic ICs. These include things like microprocessors, more commonly called as CPUs, the central processing units in computer parlance. You have chips like microcontrollers, you have programmable gate array chips, application-specific ICs, and so on. So there are a wide variety of logic chips around. And then you have the memory ICs. The memory ICs are those that are used for data storage. Broadly, there are two types of memory ICs that are in the market. You have what is called a volatile memory, and you have a non-volatile memory. You think about it in terms of importance from the perspective of volume of chips manufactured. There are basically two kinds. You have the DRAM and you have the NAND memory. And then the third category under ICs would be the analog chips. Now, these include things like power management ICs, RF ICs, most commonly the operational amplifier ICs, and so on. At a very simplified level, so manufacturing an integrated chip basically involves creating transistors on a piece of silicon. Basically, this happens by patterning and printing very small features on a piece of silicon using a technique called optical lithography. And then this kind of pattern is transferred to a wafer by various processes, including wafer etch and various other techniques. And then you create layers of metal wiring on a nano scale, which interconnect these transistors in various circuit configurations. Now, if you think about the applications of these integrated circuits, they are there in more devices than we would imagine around us. They have very wide applications. They are there under the hood in perhaps most of the devices that we use, electronic devices that we use every day. This includes things like your digital alarm clock or very, very ubiquitous things like maybe an electric toothbrush, things like that, to far more high-end applications. So broadly speaking, they are used for computations. They can be used for data storage. They can be used for sensing applications in various electronic devices. This includes computers, consumer electronics, communication devices, including smartphones. You have industrial electronics, communication infrastructure. So we talk about 5G base stations, for example. So some of the key, the drivers, enablers for these base stations are various kinds of chips, automobiles increasingly, and a wide variety of consumer electronics, including your refrigerators, washing machines, and so on. Now, to better appreciate where we are today, particularly in terms of how far the technology has come from when it started, I think it is worth taking a minute to retrace the path that has been taken over the last 5 decades or so. So the concept of integrated circuits, it goes back all the way to the late 1950s to the early 1960s. In the late 1950s, around 1958, 1959 or so, the integrated circuits were invented at Texas Instruments and simultaneously at Fairchild Semiconductors in the United States. Um, in this particular industry, the pace of technology evolution was actually set very early on. There is a very famous prediction which is called Moore's law. People in the know in the semiconductor industry and also people outside the semiconductor industry, they might be aware of the Moore's law. Um, the clairvoyant part of it is that it was presented as early as 1965, which is only 5 or 6 years after the invention of the semiconductors. But it has really set the clip of technology development, the pace of technology development for over more or less for over five decades now. So this law basically predicted that the number of transistors in a chip. So as I mentioned earlier, an IC is nothing but a collection of transistors. So it predicted that the number of transistors in a chip would double approximately every 1.5 to 2 years. So in many ways, this rule of thumb, so to speak, has been the guiding light for technology advancement, R&D efforts, capital outlay across the industry, and so on, for over five decades now, which is pretty. The longevity of this law is pretty amazing. Now, the microprocessor was, which has become the heart of computers and various kinds of electronic devices. We more commonly know it as CPUs. So this was developed in the 1970s. In many ways, they helped enable and accelerate the personal computer revolution. The Intel x86 architecture, which in some form or shape it continues to be used in chip design for logic chips today. This was also invented in the 1970s, and then the first commercial DRAM chips or memory chips they were produced in the 1970s as well. But the real growth in terms of rapid advancement of technology as well as kind of advancement in business models, um, it happened in the next couple of decades, 1980s and 1990s. I will talk more about the business models and how it has helped shape the semiconductor industry as it stands today. But basically, this era from the 1980s to the 1990s, the semiconductor market was primarily driven by demand from personal computers and later the internet. Now, in the last 2 decades, in the 2000s and 2010s, the PC market it still has a substantial share, but it has more or less matured. And a variety of electronic devices of various forms and various form factors, such as mobile phones, tablets, and so on, as well as other applications, including internet-related applications, such as networking technologies, data centers, these kind of things. They have taken over, they've more or less become the growth drivers for this market. Increasingly, automotive electronics, industrial electronics, they've also started driving this market in the last couple of decades or so. In addition, it has also seen a shift in the manufacturing center of gravity from the United States and the Western world to Asia. And increasingly, the technology leadership positions have also shifted to Asia. I think it is instructive to illustrate how we have evolved in technology by simply looking at the transistor counts on some of the chips across a time frame. If you look at the Intel 4004 chip, which was essentially the first microprocessor commercially introduced in the market, it had a mere 2,300 transistors in a chip. This was introduced in 1971. The Intel Pentium processor, which was introduced in the mid 1990s, around 1995 or so, it had, in contrast, it had about 3.3 million transistors in a chip. Orders of magnitude higher than where we were a couple of decades ago. And if you look at the current leading nodes and leading technology, what is known as a 5 nanometer technology, one of the chips produced on this technology is the A14 chip that goes into high-end Apple products today. This has 11.8 billion transistors in a chip, substantial improvement over 4 or 5 decades. That is sort of a testament to the innovation that has happened. The key part of this is that what this transistor count translates to is that it translates to a rapid increase in the chip and device performance over generations, which has led to much of the, it has been one of the enabling factors, I would say, much of the digital revolution that we see around us. Now, what does technology evolution mean in the semiconductor parlance? So the key challenge in technology scaling in semiconductors is, how do I increase the number of transistors in a chip without unduly increasing the size of the chip? So basically, I want to increase the transistor density, or the amount of transistor that I can cram in a chip per unit area of the chip. So this generally means that when you want to accommodate more and more chips in a given area, and more transistors in a given area, this generally means that the size of an individual transistor, it has to be shrunk generation over generation. So we give numbers to these technology nodes in terms of nanometers. So we talk about 10 nanometer technology, 7 nanometer technology, 5 nanometer technology, and so on. This provides some indication of the minimum feature size that is printed on a chip, or the minimum transistor size that is printed on a chip. Now, the leading edge technology today is the 5 nanometer technology. The graph on the right of this slide that I'm sharing now, this shows the transistor count trend, and across multiple products, including the memory products, including logic ICs, and so on. We can see that the number of transistors has been steadily increasing across most of the major product types for over 5 decades now. So the most advanced node in production, like I said, is the 5 nanometer chip. Some of the Apple very high-end products, the Huawei Kirin 9000 chip, which goes into high-end Huawei phones. So all of these are actually now produced on this leading edge of technology. Let us talk a little bit about the semiconductor value chain. Now, the leftmost part of the value chain, it starts with defining a product definition, and chip design. Chip design essentially involves designing the integrated circuitry. And then the circuit is basically passed on to chip manufacturing, at a wafer fabrication facility, or what is known as a wafer fab, or simply a fab in industry parlance. Manufacturing a chip, it requires various kinds of inputs. These would be things like high purity, single crystalline silicon wafers. This forms the substrate on which the chips are formed. It involves various kinds of highly specialized equipment, as well as electronic grade chemicals, which are basically high purity chemicals, gases, and so on. Now, the silicon wafers, there are two sizes of wafers that are processed in the semiconductor fabs. They have distinct equipments. The wafers can be either 200 millimeter wafers or 300 millimeter wafers. These are the two sizes that are commonly used in commercial fabs of today. It depends on the product, it depends on the technology node. And depending on your chip design, you can have as many as 50 to 1,000 dies on a single wafer. And usually you manufacture in batches of 25 wafers per load. Now, in the just to give an idea, in the figures that I have in the bottom, the middle figure especially, this is a wafer after fabrication in a fab. So the chips have been constructed, the transistors and the metallization has happened on these wafers. Now, every square that you see on this wafer is actually a chip. Now, each of these chips will actually be, they will be diced, they will be split out from the wafer, and they will now go into a packaging or an assembly process. Now, this involves basically bringing the chip to a form, um, giving it adequate mechanical stability, thermal stability, and so on, and bringing it into a sort of a macro scale or a form where you can mount it on a printed circuit board or a motherboard. Now, this motherboard is what goes into your final device in your applications, whether you're looking at a smartphone or you're looking at a PC, and so on. So if you look at a modest scale commercial fab today, they would process at least, say, 20,000 to 30,000 wafers in a month. The large fabs, the high volume manufacturing fabs, they call it the giga fabs. They can manufacture as high as 100,000 wafers a month. And each wafer would have, say, 50 to 1,000 wafers, a very broad range of wafers depending on the chip size. So you can imagine that this is a very high volume game here. Now, the wafer fab process, that is going from the blank wafer, blank silicon wafer to going to completing the fab processing and completing the transistor fabrication, the metallization part. This is a fairly lengthy process from wafer in to wafer out of the fab. It can take 2 to 3 months, depending on the exact processes. You can have anywhere from, say, 1,000 unit steps to 1,500 unit steps. There are several building blocks that are repeated over and over again in various sequences to form structures on the wafer. Some of the most common processes that are used are what is called photolithography. This is the one that patterns designs on the wafer. Etch, thin film deposition, growth, implantation, chemical mechanical planarization, and so on. And each of these have their own process complexities. Now, in the semiconductor industry, the companies usually follow one of four business models. There are, you can think of it as four types of companies in existence. I list and I sort of provide some kind of a description of what each means in the table on the left. There are companies that are known as integrated device manufacturers, or IDMs for short. Now, these are companies that include the likes of Intel, Samsung, most of the memory chip makers, they fall into this bracket. The analog chip makers, IC chip makers, people like Texas Instruments and so on, the large players, they also fall under this bracket. And there are a few logic chip makers such as Intel who are also follow the IDM business model. And what IDM means is they participate in the value chain all the way from product definition, product development, often until assembly and testing. So they will engage in the value chain all the way from defining a product, designing the chip, manufacturing the wafer itself, and often assembly and test facilities as well. There is the second category would be the fabless chip makers. Now, these are people who engage in product development, chip design, but they do not own fabs. They do not own the manufacturing facilities. These include some large names such as Qualcomm, NVIDIA, increasingly companies that would traditionally be thought of as end-use customers: Apple, Amazon, Google, Huawei, MediaTek, which is a large Taiwanese fabless company. So all of these companies, they design their own chips, but they don't have manufacturing facilities. They outsource the manufacturing to what are known as foundries or pure play foundries. Now, the pure play foundries, which I list third on this table, they are people who engage in manufacturing and sometimes assembly as well. Assembly means the packaging part of the value chain. Now, these include companies such as TSMC. Samsung is an interesting company. For certain products, it acts as a foundry. For certain products, it manufactures on its own. Largely the memory chips it manufactures on its own. The logic chips, it acts as a foundry. You have American companies like Global Foundries. SMIC is a large Chinese company. It is also a pure play foundry operating now. The fourth kind of business is the OSAT, or the outsourced assembly and test. Now, these are companies that engage in assembly and test only. So they don't manufacture the wafers. They acquire the wafers from the foundries or the IDMs. Then they would dice up these wafers, and then they will assemble and package these wafers. And then they will sell it to either PCB assembly companies or to component makers. So these are called OSATs, or outsourced assembly and test. A large part of this is in Asia. You have companies like ASC Technology Holdings, Amcor, JCET. They have large operations in countries like China, Taiwan, even Singapore, and so on. The graph on the right that I show, the top right graph here, I'm showing the percentage IC sales split into the fabless makers versus the IDM over 2 decades of time. The fabless makers is the blue line, the IDM is the red line. Now, as you can see, the more and more companies are starting to move away from owning their own fabs to a fabless model because of various complexities. Companies might not have the economy of scale for it to make sense to have a fab. The technological complexities might be not worth their time or capital to invest. So they might choose to move to a foundry and to a fabless mode. The bottom two pie charts, I talk about the sales for IDMs, or the integrated device manufacturers, and the fabless companies. This is organized by headquarters. So this is a geographical representation organized by headquarters. US is an important force in both IDM and fabless. If you look at it by headquarters, that is, there are a lot of American companies that are in the market today selling IC chips. Now, this is an important point to keep in mind, because I will present a drastically different picture when I talk about production. Now, having headquarters, being an American company, does not mean that the production is happening in the United States. You will find that a large part of this production might be happening elsewhere, largely in Asia. This is a point to keep in mind. Now, in the next slide, I talk about production patterns. I will now go to discussing production patterns, consumption patterns. Now, talking about the production patterns, the monthly global installed capacity has been growing at the rate of 5% per annum from 2010 to 2020 at a rather steady clip. If you look at who are the largest players, if you look at it by country, you will find that much of this manufacturing is happening largely in Southeast Asia. Mainly 4 countries. You have TSMC, Samsung. You have certain Japanese companies. Kioxia is actually a spin-off of Toshiba. You have Chinese companies. There is SPIC, which I alluded to earlier. There are also a lot of multinational companies that have invested in China. Companies including Intel, TSMC, Samsung, companies like SK Hynix, which is a large South Korean memory maker. All of these companies have also invested in China. So if you think about the key producers, there are really 5 countries to look at. One is South Korea, Taiwan, Japan, United States, and China. And now if you look at it by product, that is installed capacity by product, what product are we manufacturing with this installed capacity? You'll find that the largest volume goes to memory. That is almost 39% of the installed capacity is dedicated to memory manufacturing. This is memory is a sort of a low margin comparatively in relative terms compared to some of the microprocessors and other logic chips. This is a lower market, very high volume product. It goes in starting from commodity products like your flash drives and your USBs, all the way to data centers and highly sophisticated products, your SSDs, your solid state drives, and so on. All of them need data storage. So it is a very high volume product. Then following this, you have foundries, which largely focus on logic ICs. Because generally the memory and analog IC makers, they will not outsource their manufacturing. The logic IC, the design is fairly complicated. So the companies choose to specialize. So a lot of foundries, they will manufacture logic and sensor chips. So a large part of the installed capacity, almost 37%, is in foundries. And then analog has about 9%, and other products can have about 5% and so on. Now, if you look at it by what country is producing what product, where it has dominance, South Korea by far leads in memory. So I talked about two kinds of memory. You have the DRAMs and the NAND memory. South Korea has substantial presence in both of these. Uh, Basically, two companies. You have Samsung and you have SK Hynix. Both of them command a substantial market share. Again, there are also other companies. There is Micron, which is an American company. There is Kioxia, which is a Japanese company, and so on. But a substantial portion of the market share is shared by the South Korean companies, Samsung and SK Hynix. And then Taiwan, it leads the logic foundry manufacturing space. Now, one of the key insights to take away from here is that only 12% of the manufacturing is actually happening in the United States. This is down from about 37% in the mid 1990s, 1995 or so. This is data from the Semiconductor Industry Association. This might be an important figure to keep in mind as I talk about some of the trends in thinking now that is happening in countries such as the United States and Europe, and how they are viewing semiconductor manufacturing and sort of its strategic relevance in recent times. The foundry fabless landscape is a fairly interesting business model that has sort of been revolutionary in many ways in advancing the cost of the semiconductor industry. So I want to take a minute to examine the foundry fabless landscape in a little bit of detail. Now, nearly 64% of the foundry business, so foundry again are companies that specialize in manufacturing. They take the chip design from the fabless companies and they manufacture to order. They're essentially contract manufacturers. Nearly 64% of the segment is run by Taiwanese companies. The largest of these Taiwanese companies is what is called TSMC, or Taiwan Semiconductor Manufacturing. And then the second largest in the space, there's quite a gap here, is Samsung, which is the South Korean conglomerate that does a lot more than just semiconductors. So together, these two companies, they command about 79% of the foundry market. And then China has some presence, 6% as well. And others others is about 15%. Even when you're talking about the others, there are a few Asian companies in this mix. For example, Tower Semiconductor, which is an Israeli company. It is a fairly large player in the space, albeit in perhaps in older technologies, but it's still by volume, it is still a substantial player in this space. Now, companies have increasingly shied away from manufacturing due to various reasons: technological complexities, R&D and periodic capital investments required, not having adequate capacity needs, which may not justify these kind of investments for them. They don't have the adequate captive use to justify these kind of capital investments. For example, this graph from McKinsey here, it shows the exponential rise in the cost of fab construction with increasing technology nodes. For example, McKinsey has calculated that setting up a 65 nanometer fab, this is just the fab construction, it does not include equipment and other things to equip the fab. Just from the perspective of fab construction, it can cost about $0.4 billion to construct a 65 nanometer fab. Whereas if you look at the leading edge of technology, which today means 5 nanometer or 7 nanometer technology, this has an exponential rise. It can be as high as 5.4 billion US dollars. This could be prohibitively expensive for many companies that don't have the economy of scale to justify these kind of costs. Now, if you add to this the cost of sustained R&D required, capital equipment required, the cost of a fab, again, I'm talking about the leading edge fabs, it can run into tens of $1 billion for a leading edge node like 5 or 7 nanometer nodes. The migration towards the fabless business model, particularly by companies in the United States, it's had two effects. Number one, at least in the last few years, you're increasingly finding that the companies that would be traditionally thought of as end product, makers, OEMs, such as companies such as Apple and Huawei and Tesla, Volkswagen, Google, Amazon, all these companies have now turned into chip designers because they don't have to manufacture the chips. They are able to design the chips. They get them contract manufactured. So there are a lot of entrants into the fabless space. The second effect is that the manufacturing of key products, particularly various kinds of logic chips, they have increasingly become concentrated in the hands of a few countries. And now this is of relevance because it is causing concerns about supply chain vulnerabilities, particularly in the United States, Europe, and so on in the last 2 or 3 years. We'll talk about this a little bit more in some subsequent slides. Now, if you look at the global consumption patterns, China comes into the picture here in a large way. The graph here on the left, I'm showing the IC sales by region. The red line here, it refers to China. The blue line here is the rest of Asia Pacific, and the rest of the world. The purple line here, I'm talking about Americas, which really means United States. A large part of it is United States. And then you have Europe and Japan at the bottom there. According to data from the Semiconductor Industry Association, WSTS, and so on, China has a 35% share of consumption in the world. The consumption in 2020 was about $151 billion in components, and then against US consumption of about $94 billion. The Chinese consumption has largely been driven by their electronics industry. They have a couple of very large telecommunication equipment makers who are focusing on 5G equipment. This drives a lot of sales for leading edge chips. They have made a large foray into electric vehicles, autonomous vehicles, and so on. So the growth in consumption in China in the last 5 years has far outpaced the rest of the world. Now, the graph on the right, I show this consumption by end-use applications. This graph goes from 1998 to a forecast for 2024. The blue bar here, it is referring to computers. The red bar here, it's referring to communications, which includes things like smartphones. In terms of the end-use applications, you can find that the PC market has more or less saturated in the last 7 to 8 years. It is basically matured. So there's still substantial demand from PCs, but it is not a growth sector anymore. Although it may have received a temporary boost from the COVID pandemic and the remote work trends and so on, with people buying, second PCs and so on for remote work, e-learning, and all that kind of thing. But the growth segments over the last few years have been communication electronics, which includes smartphones. It also includes network infrastructure and so on. And the purple bar that we are looking at here, which is basically the automotive electronics. So these have grown at a steady clip. Now, in the context of India, India's consumption overall was estimated to be $21 billion in 2019, according to the Indian Electronics and Semiconductor Association. Now, there has been a boom in mobile manufacturing, in particular, in the last 3 or 4 years. A large number of multinational companies, including companies like Samsung, Xiaomi, and so on, they've set up very large mobile phone assembly units in India. This has driven a substantial amount of this consumption. And then also the automotive industry in India, which is fairly important in the Indian context as well. Let's take a minute and look at the support industries in the value chain. Earlier, I talked about the major inputs to a fab. I talked about silicon wafers, equipment vendors, and so on. Now, although the production might be increasingly concentrated in Asia, many of the critical resources required for chip design and manufacturing. Now, that includes wafers, it includes advanced equipment. It includes EDA software, which is used for chip design. It includes electronic chemicals, consumables, and so on. These are largely being controlled by companies in the United States, Japan, and Europe. For example, one of the most critical equipment and perhaps the most expensive equipment in a wafer fab is a photolithography scanner. So this is critical from the perspective of defining the size of the transistor. This is what really enables the dimensional scaling of the transistor in some ways. Now, ASML, which is a Dutch company headquartered in Eindhoven, Netherlands. Now, this company owns nearly 70% of the market share in this space. In fact, for certain types of scanners, known as the extreme UV or the EUV scanners, which are being used in the 7 nanometer and 5 nanometer and future nodes, it is thought of as an enabling equipment to manufacture these kind of nodes. ASML holds a monopoly. No other company in the world can actually make these scanners at the moment, although they're trying. And then if you look at companies like Applied Materials, Lam, KLA, Tencor, and so on, which are all American companies, they hold a broad line of equipment that you will find in any commercial fab across the world. So although the manufacturing might be concentrated in the United States, there is a global value chain here with potentially geographic specializations, and really multiple pieces need to work together on a global scale to make a fab happen. From the perspective of India, we don't have a substantial position in any of these support industries so far. It's not surprising considering that we don't really have a fab ecosystem at the moment. So one of the most important things in a fab is sustained capital and R&D spending. So if you look at the capital spending worldwide, which is the graph here on the left, the spending here is denoted in billions of US dollars. In the last 4 years or so, the capital spending per year has been in the neighborhood of about $100 billion a year. This is the global spending cumulative of all the companies in the industry. Now, a significant portion of this, as I will illustrate more later, is actually happening in China, which is investing very aggressively in capacity creation, both to meet its consumption demands as well as strategic initiatives in China. Now, in terms of R&D spending, which is the graph on the right here, the semiconductor industry is usually next only to the pharmaceutical industry. Now, the R&D spending is extremely critical in keeping up with this 2 to 3 year technology advancement pace. And the R&D expenditure can be as high as 15% of the total revenue of the industry. For example, in 2018, the R&D spending was estimated to be around 68 billion US dollars. It's a substantial amount of the revenue of the industry. Now let us examine the scenario in China. It is growing to be a very important force to watch out for in the next few years in the semiconductor manufacturing space, not just in manufacturing, but also in the fabless segments, in the assembly segments, and so on, generally in the semiconductor space. Now, over the last 3 years or so, ICs have been the largest import for China. It exceeds other commodities such as crude oil, iron ore, and so on by value. China has a very vibrant electronics manufacturing scene, in addition to making large inroads into various types of advanced automotives, including autonomous vehicles, electric vehicles, and so on, as well as telecommunication equipment. You have large companies such as ZTE, Huawei. They specialize in manufacturing telecommunication equipment, which are all enabled by chips. It's said that nearly 90% of all the laptops assembled in the world, they are assembled in China. 60% of all the smartphones are assembled in China. So it has a substantial presence in the electronics manufacturing scene, which is really driving the semiconductor consumption in China. The problem with China is that the consumption of semiconductors is far outpacing its ability to produce semiconductors. The graph on the right here shows chip consumption versus chip production by year. The red line here is the chip consumption by year. The chip production is denoted by the gray line. And this graph here, it goes from 2009 to a forecast for 2014. You can see that the graph, the gap between the two has been increasing substantially over the years, which is causing deep concerns in China due to various reasons, including geopolitical reasons, the U.S.-China trade tensions, which is causing nervousness in terms of how I will be able to get my chips in the next couple of years, and so on. As it stands today, the domestic production of China amounts to about 15% of its consumption. Half of this is from Chinese-owned firms, that is, firms that have headquarters in China. The remaining is from multinational companies that have invested in China over years. The Chinese government has taken semiconductor industry as one of its strategic priorities, particularly starting from 2014, when it introduced its Made in China policy with substantial capital outlays for developing the semiconductor industry. China already has reasonable positions in the assembly and test markets, the OSAT markets, as well as in the fab space. They have very respectable global shares. Again, there are a number of multinational companies, including Intel in Dalian, TSMC in Nanjing, Samsung, SK Hynix, all of them have presence in China. But China has been making aggressive capital investments, very large investments, both via state-backed fundings as well as venture capital fundings in various facets, including logic chips, memory chips, analog chips, as well as creating an ecosystem. They've been investing in equipment companies, in chip design, as well as creating manufacturing capacity. If you look at the rate of growth of installed capacity, which is shown in the graph on the bottom right, it shows installed capacity by region spanning from 2012 to 2021. And the red line on this graph, the one on the right bottom, it refers to China. In the last 3 or 4 years, the Chinese capacity creation has drastically taken off. Now, this will reflect in the sales in the next few years, because a fab will take some sort of an incubation time to meaningfully achieve scale and make a mark in terms of revenue. But the rate of growth of installed capacity has been at the rate of about 14 to 20% per annum in China, far outpacing the rest of the world. Now, it is not clear whether China will reach its goal of 70% self-sufficiency by 2025, which was one of the goals set out in the Made in China policy. Whether it achieves that or not, it is very clear that China has put semiconductor manufacturing as one of its top strategic priorities for various reasons. I'll move on to the second segment of my talk, where I talk about some of the recent developments that have impacted the global semiconductor industry, which could potentially reshape the industry in some shape or form in the coming years. I will discuss 3 topics in particular. Number 1, how the technology leadership landscape has evolved over time, especially looking at the logic technology, which is often considered as a benchmark for technology advancement. This is often the technology that has the most shrink in transistor dimensions. Number 2, I will look at the global chip shortage, which is affecting multiple sectors and multiple countries, including India, with the auto sector particularly badly hit, but it's also spreading to the other sectors, and it's likely to have impact to many products that we take for granted right now. Number 3, I will talk about how semiconductor manufacturing is increasingly being viewed as a strategic priority, and sometimes from a national security lens, in language that resembles how countries talk about things like crude oil, particularly in countries such as United States and Europe, and what this could potentially mean for geographical footprint in manufacturing going forward in the next few years to a decade or so. Now, the first topic, when I talk about the technology leadership landscape, as I mentioned, logic technology can be considered to be a benchmark for process technology advancement. It has the most shrunk transistors, that is, it has the smallest size transistors in general historically. The graph here on the left, it shows the number of years behind a leader in technology. So the way to read this is, it is baselined at 0. Historically, the United States has been a leader. By United States, essentially, I mean Intel, in the logic space. Intel has essentially set the pace for technology development historically. The purple line here, it represents Taiwan and Korea. So how these two countries have caught up over time, and what lag they have in terms of number of years at a particular time in history. And number 3, the blue line here, it represents China. So if you look at the purple line here, you can see that Samsung and TSMC, which is essentially talking about Taiwan and Korea, the largest people manufacturing the logic semiconductors, they have caught up at an accelerated pace starting from 2010 to 2019. This graph is a little dated in the sense it was published about a year ago. But if I were to extend this graph to 2020, when the 5 nanometer technology came into volume production, you will find that TSMC and Samsung, they have outpaced Intel in terms of the ability of Intel to manufacture or to lead the technology space. So currently Intel might actually be 1 year behind. The United States might be 1 year behind in the logic space. Now, the graph on the right is talking about how many players in the world can actually manufacture a certain technology node. The far left bar here, where I talk about 25 players, this is talking about the 130 nanometer technology, where you have a substantial number of players, about 25 players in the world who are able to manufacture. This translates to many, many fabs across the world. But as you go down to the far end, to the leading edge of technology, it drops down to 2 kind of players, essentially leaving 3 people in the scene who are able to manufacture technology that is in the far end, that is in the leading edge, which is essentially Intel, TSMC, and Samsung. And increasingly, it looks like Intel and it looks like TSMC and Samsung for the 5-3 nanometer kind of technologies. Now, this really indicates that the center of gravity for technology leadership has gradually moved from the United States to the Asian countries in Taiwan and South Korea. Now, why is this of relevance? Why does it matter? It matters because it is leading to some concerns in the United States about how they are thinking about this technology. So the United States government has requested TSMC to set up a 5 nanometer fab in the state of Arizona. So TSMC is investing in a 5 nanometer fab. The word is it may not be just one fab, it may be a cluster of fabs. They've acquired land that is sufficient for 5 or 6 fabs in the state of Arizona. So this is definitely causing concern in the United States that they may not be on the leading edge of technology, and they want that manufacturing footprint to remain in the United States. Now, the second thing I will talk about is the global chip shortage. It's crippling recovery from COVID, particularly for the auto industry. But increasingly, it is also affecting several other industries like consumer electronics. Companies like Samsung, Sony, and so on, they have, companies like Samsung, they have said that it is going to affect their appliance manufacturing. Includes things like televisions, washing machines, refrigerators, and so on. Sony very early on said that it has affected their PlayStations, PS5 manufacturing. Apple has said that it is likely to affect the iPhone manufacturing. Industrial machinery makers, they have reduced revenue guidance. So it is not just the automakers. The automakers have certainly been hit very hard, but it is also spreading to many other sectors at the moment. Now, what is causing this? Initially, it was blamed on COVID. There was certainly a surge of demand for consumer electronics, PCs, other things. PCs actually received a boost of life during COVID because of work patterns. More and more people, they had to buy second and third systems. They were working from home. They had to cater to their children who had to study from home, e-learning, and so on. People were not able to take vacations. They had some sort of discretionary income, so they invested a lot in gaming systems. If you think about companies like Netflix, streaming services, they showed a surge in profit, a lot of new subscribers to things like Netflix, which in turn drives demand for data centers and so on. Internet traffic substantially increased during COVID, which in turn drives demand for data centers, hyperscale servers, and so on. And coupled with this, the auto sector, particularly starting from Q3 2020, it experienced recovery that was better than expected. Um, the automakers have certain problems in the sense that that is probably not there for the other companies, in the sense that they don't necessarily they practice lean principles. They practice just-in-time manufacturing principles, which means they don't have large safety stocks. They ended up canceling orders during COVID, which were then moved to other product lines. And when the recovery happened, they're kind of caught with their pants down, so to speak. But increasingly, it is becoming clear that it is not just COVID that is causing this chip shortage. Some chip companies, like TSMC, for example, they've stated that China has been stockpiling chips, particularly because of the geopolitical uncertainties. There have been so there has been increasing tensions between US and China in the last 3 or 4 years, starting from the end of 2017. And one of the things that has happened is US has placed certain companies such as Huawei and SPIC, which is a foundry company, on what is called an entity list. This is basically meant that companies that use US technology, whether it's equipment, whether it is software, they should not actually be selling to China, to the companies on the entity list. Now, what are the companies that use US technologies? The value chain is really globalized, which means every company. So every company will use ASML scanners. Every company will use EDA software that is dominated by the US markets. So multiple companies, for example, TSMC, they have been unable to sell to China. Companies like Micron have been unable to sell to China. Now they are able to sell to a certain extent with special licenses, but for a large part, for many of the product lines, they've been unable to sell. So Chinese companies that are not on the entity list, they've also been subjected to they've also experienced certain kind of uncertainties, which has kind of led to a panic, and they've been stockpiling chips, as well as capital equipment, actually, in the last 2 years or so. So the chips, for example, about $350 billion worth of chips was bought by China, imported by China in 2020. There are secondary factors. There was a fab closure for 48 hours or so by fabs that operate in the Texas, Austin area, Samsung, NXP, and so on. Now, why is this important? NXP and Infineon, which are European companies, they're Netherlands and German companies. Now, these companies are some of the largest chip makers for the auto sector. So a 48-hour power disruption in a fab because of a winter storm, it can have a substantial impact to production. There have been secondary factors. There has been a packaging substrate material shortage and so on. So it's not really one factor. Multiple factors have contributed to this to the shortage. One perhaps exacerbating the other. Automakers also have particularly vulnerable positions. There are two things. One is I talked about the just-in-time manufacturing. But the other thing is that it is not very easy to ramp up auto chip production in a semiconductor fab as opposed to some other kinds of consumer chips. Why is that? Because the product quality reliability specifications that are required for an auto chip. For example, if you guarantee a chip for 7 years for a consumer chip, you may have to guarantee that a chip will work for 15 years for an auto chip. An auto chip, for example, has to function at a much broader range of temperatures compared to a common consumer chip. This means that ramping up production in a fab for an auto chip is substantially more difficult compared to other kind of consumer chips. So not all fabs are qualified. It takes 6 months to a year to actually bring a new fab online to produce auto chips. So ramping up capacity overnight, it's possible to a certain degree, but it cannot be done as quickly as possible due to some of these reasons. So this is definitely going to take some time to iron out. Some people predict 12 months, some people predict 18 months, some people have predicted until 2023. But for sure, this is going to take some time to iron out. This is going to cause a lot of pain, a lot of concerns about supply chain vulnerabilities. It has been estimated that about 5 to 10% of production is going to be hit. Some people are going with features that they can say do away with. For example, some companies are saying that they will not have, say, fuel management ICs. They will not have navigation systems in some of their chips and so on. So these kind of short-term measures are happening, but this is going to be a pain point for some time in the future. The third thing I'm talking about, in some ways, it is related. It is the reshoring of semiconductor manufacturing. This is a new term that has been coined in the business parlance in the last few years or so. They're calling it reshoring of semiconductor manufacturing, which essentially implies bringing back semiconductor manufacturing to certain countries in the West. Now, increasingly, you have countries around the world, they're recognizing that semiconductors are a critical part of the supply chain. Foreign dependence, lack of control on manufacturing, that it could have certain disadvantages from a long-term strategic standpoint. This graph on the right was published by the Semiconductor Industry Association in the United States in 2019 or so. This projected that over the next 10 years, 2020 to 2030, most of the capacity creation will happen in Asia. A substantial portion of this will happen in China, and the US share in production will further erode to about 10% or so. Europe has been particularly affected by the automotive chip shortage. Some of the largest auto chip companies, as well as the automakers, the OEMs, they are located in Europe. It is estimated that about 34% of the auto chips, they go to European companies. But the problem is the auto chip makers in the US, they also, while they could be manufacturing some of the chips, many of the leading edge chips, they actually outsource to foundries that are located in Taiwan or South Korea. Now, this has led to significant concerns over foreign dependence on chips in an industry as valuable to Europe as automobile. And there have been increasing calls, sort of panic calls, for bringing back manufacturing to Europe. For example, just a couple of months ago, Europe has released what is known as the Digital Compass Plan, where one of the things it has said is that it wants to set a target to increase Europe's global market share to about 20%. It is recognized that this might require investments as high as $100 billion over the next few years. Intel, which actually has a presence in Ireland, it is said to be in talks with the European Union to set up a bleeding edge fab, which could mean something like a 7-nanometer fab. And it has asked for subsidies amounting to about $8 billion from the European Union. There is also an industry alliance across multiple countries in the European Union which have a significant presence. Countries like Netherlands, Germany, France, and so on, which have manufacturers, they have equipment makers. An industry alliance is being considered for setting up a fab as well. Now, from the perspective of United States, they passed something called the Chips for America Act in 2020. The United States has recognized that semiconductor manufacturing might be one of the strategic pillars, that it is a critical part of the supply chain. Some degree of control over manufacturing might be required. And has also recognized that some of the countries in Taiwan, China, and so on, um, they have received incentives from the government, which has perhaps incentivized them to to invest capital expenditure as well as R&D, which has helped them substantially grow their capacity over time. And US has somewhat lagged behind from this in this perspective. There are also geopolitical risks that around Taiwan. Taiwan controls a substantial portion of uh, the foundry market, which locks up a variety of logic chips. Taiwan is really considered to be a breakaway territory by China. China definitely seeks to reunite Taiwan someday. So there are certainly geopolitical risks about Taiwan and how companies such as TSMC and other companies, UMC and so on, which is also another large foundry in Taiwan, how this could disrupt. Should China seek to move in some way, say militarily in Taiwan, how this would disrupt the supply chain and what degree of control the United States might have over securing its supply chain. This has led the United States to do two things. Once, it has asked companies such as Intel to increase investment in the United States. So Intel has announced a $20 billion investment in the United States. It has also led the United States to request TSMC to set up a 5 nanometer fab in the United States. It certainly wants to have a footprint in some of the leading edge technology. It considers that important. So TSMC has acquired enough land to set up one or more 5 nanometer fabs, which is expected to become operational by 2024. Now, how much of this is going to actually reshape the potential production landscape in the future? This remains to be seen. But I think it certainly reflects the kind of thinking that is going on in the United States and Europe at the moment. Now, I will talk about the future trends in semiconductors. What is going to drive the semiconductor industry in the next decade or so? This graph on the right, I show the amount of data generated and consumed in a year as a function of time. Now, I don't know about the others, but I have a hard time fathoming what exactly a zettabyte means. I cannot wrap my head around this. But all I know that it's a gigantic amount of data. A zettabyte means a trillion gigabytes. And the amount of data that is being consumed, generated, has been substantially increasing, and it's projected to increase exponentially until foreseeable future. The world is essentially swimming in data. What does this mean for the semiconductor industry? It is going to increase the need for data centers, which is essentially the backbone of the internet. This is going to, what does the data center rely on? It relies on chips like the CPUs. In fact, the high end of the CPUs, graphic processing units, some of the logic chips, is going to drive a substantial need for data storage and retrieval, which means it is going to drive the memory industry and so on. Increasingly, companies are looking at digitalization, cloud adoption, and so on. This is going to drive the need for compute and memory chips. Automotive industry, it is estimated that about every car on average by 2022 will have around $600 worth of IC content in a car, which is nothing to sneeze at. A substantial portion of the cost of the car will be the integrated circuit. Electric vehicles, which are seeking to make inroads, autonomous vehicles, and so on, they can have as high as 2x of the semiconductor content. Now, this ranges from low-end chips. You can have standard commodity chips that are used in, say, fuel management and so on, which is manufactured on older technologies, to some of the leading-edge chips on the high-end cars. There are other new application trends. Swaminathan earlier, he referred to Internet of Things, industrial Internet of Things. It's essentially a web of interconnected devices. This trend is going to take off. 5G networks. This is going to have two effects. You need to build the network infrastructure, which means you need to build the base stations, the receivers, and so on. This is going to drive the need for chips. You need to build 5G enabled devices, smartphones, tablets, and all that. That is going to drive the need for chips. But also autonomous vehicles, artificial intelligence, and all this. So the semiconductor industry per se, it is going to have a fairly vibrant future. The PCs may have saturated, the smartphones they will potentially saturate, but there are going to be a lot of new application trends that will drive this market. The next slide, I kind of illustrate this with some data. The growth forecasts is provided by ASML, where they project what will be the growth for each of these end-use segments in 2024 compared to 2019. I will not highlight everything here, but if you look at the servers, data centers, and automotive, so these are the kind of sectors that will grow at a substantial pace over the next few years. If you look at segments like personal computing, they will still have a substantial share, but they will perhaps grow at a lower pace, about 3% per annum. So now I would like to start looking at the scenario in India. India continues to be, it is currently 100% import dependent for components. In terms of the semiconductor components alone, that is not including electronic devices, which are in the assembled form, which are imported in the assembled form, just the components, what is imported as integrated chips. This component import value in 2019, 2020 was estimated to be about $10.1 billion. It has taken a substantial jump around 2018, 2017, 2018 timeframe, mostly driven by the mobile phone manufacturing boom. When a large number of when certain companies such as Samsung and Kioxia and so on, they set up very large mobile assembly units in India. So at the moment, India is the second largest manufacturer of mobile phones. There are said to be over 200 assembly units. It includes local manufacturers, it includes multinationals. Perhaps one point of concern to some Indians might be that 70% of the ICs today, they're imported either through China or Hong Kong, which amounts to about 7.1 billion US dollars. Because of the political sensitivities around these countries, this might be something of concern, particularly considering the growing stature of Indian electronics industry. India's main contribution, and perhaps a substantial contribution to the semiconductor industry, has been in chip design. India has had a presence in chip design for over 3 decades now, starting from some of the initial investments made by Texas Instruments in the 80s and 90s in India. If you look at who has invested in India, many of the major multinational semiconductor companies, including companies such as AMD, Intel, Qualcomm, Texas Instruments, MediaTek, which is a large Taiwanese design company, fabless company, they all have design outfits in India. EDA companies means the companies that design the software used for chip design. So these companies also have a substantial presence. Most of them are around the Bangalore, Noida, Hyderabad, those kind of regions. There is also a startup ecosystem, and many homegrown companies, either on their own or with joint ventures with some of the foreign fabless companies that are starting. Now they work on a range of chips. It could be low-end chips, but they are also working on fairly advanced technologies, including chips for 5G applications, Internet of Things, system on chip designs, and so on. So there is a high degree of competence in this space in India. The Indian Electronic and Semiconductor Association, the IESA, which is basically a conglomerate of, which is basically an assembly of multiple electronics and semiconductor companies. Semiconductor in the Indian parlance essentially means these fabless companies. It has valued the Indian semiconductor design industry to be about $23 to $29 billion in terms of the contribution that they provide to the overall semiconductor company. overall semiconductor industry. Now, one thing we have to do is we have to very carefully distinguish this success from India's position in manufacturing. In contrast with the semiconductor design, manufacturing has not made significant inroads. In India, when we talk about semiconductors, we tend to lump everything together. Now, semiconductor design is substantially different from manufacturing. There are no commercial operating fabs in India currently. There is the Semiconductor Laboratory, which is owned by the Department of Space. It operates a 180 nanometer technology fab in the Chandigarh area. It produces logic chips, mostly for captive use, but it's not a commercial fab. There are a couple of fabs that are owned by DRDO. One of them is a compound semiconductor fab. So I earlier mentioned that you can either manufacture ICs on silicon, or a minority of the semiconductors are manufactured on compound semiconductors. Gallium arsenide is one of them. And this fab, it's a GATEC fab. This is in Hyderabad. This is the gallium arsenide fab. This operates 150 millimeter. So these are not commercial scale wafer size. These are smaller wafer size fabs. They operate, they generally cater to legacy technologies, mostly research fabs in some cases. There are also research level clean rooms in certain institutions such as IASC, IIT Bombay, and so on. But essentially, these are not commercial fabs. They are fabs meant for research or for some sort of captive use. Again, as Swaminathan mentioned earlier, going back to the early 2000s and perhaps even to the late 1990s, there has been periodic, sort of sporadic interest in setting up a fab in India. In recent times, in the last 5 or 6 years, there have been at least 2 proposals that have made news to set up a fab in India. One is in UP. It was supposed to be a partnership between Jaiprakash Associates and IBM and Tower Semiconductor, which is an Israeli foundry company. And then the second one in Gujarat, it was meant to be a partnership between Hindustan Semiconductor, ST Microelectronics France, and Siltera, which is a Malaysian company. For various reasons, both of these projects are not in consideration anymore. They have fallen through. They've essentially been non-starters. But in 2020 December, recently, the government of India has issued an expression of interest to receive proposals, one of which is to set up a 28 nanometer or a better fab. It has stated that it would like to set up a fab with a foreign investor with potentially an Indian partner. The deadline for this, for receiving proposals for this, was April 30th, and this is something to watch out for in the near future. Now, a valid question arises as to why India should invest in a fab in the first place. It has substantial competence in the design sector. Why should it not simply specialize in the fabless space? Why should I invest in a fab in the first place? Considering many of the things that I talked about, including capital outlays required, R&D, and so on, and not to mention the technological complexities that happen. Now, perhaps one way to evaluate the question is to consider, from a long-term perspective, what exactly are India's ambitions in industries where chips form a critical component of the supply chain? For example, what are India's ambitions in the electronics, automotive, consumer appliance, and other end-use segments? I will look at 2 things. If you look at electronic system market in India, now it is projected to grow to a value of about $160 billion by 2025 at a fairly rapid clip of 14% CAGR. It has grown at a fairly rapid clip of 14% CAGR from 2016 to 2019. Starting around 2017-2018 timeframe, India is now the second largest manufacturer of mobile phone handsets in the world today, next only to China. A number of large smartphone makers, like I mentioned earlier, Samsung, Xiaomi, and all of them, they've set up manufacturing facilities in India. In fact, Samsung has its largest mobile phone manufacturing facility in Noida. It is not anywhere else in the world. It is in India. Now, India is certainly looking to replicate this success in other electronics segments, going by some of the recent policy initiatives and the incentives that have been announced, particularly in laptops assembly, tablets, certain consumer appliances, and so on. For example, there have been agreements signed with Panasonic for setting up refrigerator plants in India. One thing that we must keep in mind is that many of these factories are assembly units, which means that they import a majority of the components, including the ICs, the LCD displays. There is some lithium battery production in India, but a substantial portion continues to be imported. By some estimates, it is estimated that if you look at the value of a phone in terms of how much has been contributed by Indian components, the contribution from India in the value of a mobile set is about 12%. The rest is essentially imported. In terms of, again, consumer electronics and appliances, India targets to be the fifth largest producer in the world. There's nothing to sneeze at. It is quite a substantial position. Now, if you look at the automobile industry, India today is the fourth largest producer of passenger vehicles in the world. It's a very respectable position. It has targeted 15% electric vehicle adoption by 2030. We've seen a number of initiatives, joint ventures, both by local companies such as Mahindra, as well as certain multinational companies. They're also being announced. Now, a second way to look at the question of whether India needs to set up a fab, why it needs to set up a fab, is to look at it in terms of the captive demand that could happen from the fabless design ecosystem that India has been building, and that it certainly has a great interest in building going forward as well. There is a sort of a startup ecosystem that is happening in India. Now, this could be a captive market for a fabrication facility in India. There are said to be around 120 companies in semiconductor design. Thirdly, very simply from a strategic standpoint, looking at it from a simplistic standpoint, we have to really answer the question of whether we are comfortable with having 100% import dependence on a critical component such as an IC, which forms a very valuable part of the supply chain in the electronics and automobile industry. That is, do I have ambitions to build these kind of industries without a strong foundation in securing my supply chain? This certainly, even from a simplistic standpoint, it exposes India to a deep supply chain vulnerability. And in my opinion, India should certainly consider investing in a fab and certainly consider expanding on it, simply from the point of view of securing its supply chain from a long-term strategic standpoint. Now, this kind of thinking it appears to be recognized by the policymakers now. There was a revised national electronic policy released in 2019, which sort of replaces the policy of 2012. This aims to grow the electronic system design and manufacturing, what is called the ESDM sector in India. Aims to grow this sector by up to $400 billion in value by 2025. This includes various kind of things. It includes various kinds of electronic components and design. This policy also explicitly recognizes the need to break into semiconductor manufacturing. One of the key missions of this policy is to secure the electronic supply chain and develop capabilities for manufacturing components, including ICs, among other things, such as LCD displays and so on. Now, in support of this national electronic policy, a few other incentive schemes have also been announced. This includes schemes like what is called SPECS now, the production-linked incentive, what is called the PLI scheme right now, which covers the semiconductor industry and the assembly and test industry, in addition to the broader electronics and fabless industry. Now, let us look at the opportunities for India in the semiconductor space. I think we have to recognize certain ground realities in India today. Although there are smaller scale fabs, there are clean rooms in India, we do not have the experience in running a commercial fab. A commercial fab is more than technology, and India is a late entrant into the space. while you have a large pool of engineers in India, the engineering pool in India is not necessarily trained for the semiconductor industry or semiconductor fabrication in particular. To be fair, there has been no need to train this pool. This has to come over time. But the fact remains that that to run a large fab, you need a substantial pool of engineers, skilled engineers who are actually trained in this industry. There's some sort of scheme to train. Now, there have been initiatives in certain universities to introduce semiconductor training, microchip fabrication training, but really without an application sector within the country, I'm not sure how much sense it actually makes. There could be capital infrastructure consideration, particularly two things I would like to call out. One is power requirements. Semiconductor industry requires substantial amount of power. It requires undisrupted power. A power disruption in a semiconductor fab, considering the value of the equipments that is in the fab, considering the amount of time it takes to bring online the fabs after power disruptions, it does not make sense to for a commercial fab to have these equipments idled for any length of time. So undisrupted power is certainly one of the infrastructure considerations that is required. The second is high purity water. What we call in industry parlance is UPW or ultra pure water. So these kind of considerations, there's a perceived notion that India may not have some of these infrastructure capabilities. Government may need to assure that some of these capabilities exist and India is capable of running some of these fabs on a commercial scale. If you go from the technology perspective, the most advanced technology that India is running at the moment is the 180 nanometer technology that is not on the commercial scale. So, like I said, running a commercial fab efficiently is more than simply the technology itself. There are a lot more components that go into it. So there is, even from a technology space, there is a steep learning curve that needs to be overcome. Now, the best bet for India would be to persuade an established chip maker to establish a fab here, perhaps with partnership from an Indian with an Indian partner. Secondly, I'm not proposing anything new here. A number of analysts who actually look at India, they proposed something along similar lines. India might do well. It might be set up for success in this area by investing in a mature technology. I mentioned two wafer sizes that are produced commonly in commercial fabs. You have the 200 millimeter wafer size and you have the 300 millimeter wafer size. The technologies 90 nanometer and above are generally fabricated in a 200 millimeter wafer size. And the technologies that are below this, the 65 nanometer and below technologies, are usually fabricated in a 300 millimeter wafer. Now, investing in a 200 millimeter wafer fab on a mature technology, it might be a suitable and a quick starting point for India and set it up for success, set it up for a viable learning curve in order to expand into other more advanced technologies in the future. Now, when I talked about this to someone, they asked me if I was asking to move from an airplane to a bullock cart. But that's not it. That's not the point here. Again, like I said, this has been proposed by a number of other analysts as well. To illustrate what I mean here, the graph here on the left is showing the foundry market by feature dimension. And this projects all the way out to 2025. If you look at this, there is going to be a steady demand. The green bar here and above, it is talking about the 90 nanometer technologies and older. There will continue to be a steady demand for older nodes. It is said to be perhaps about a $40 billion industry if you consider everything. Even today, there are fabs that are coming up in other countries in 200 millimeter wafer size. Most of the foundries around the world, they operate both 200 millimeter and 300 millimeter fabs. So I'm not really saying that we have to go back to a bullock cart, but I'm saying that we will really set up the country for success if we were to invest in this kind of a technology and get a learning from this technology in order to advance to other nodes. In terms of application, you still have ICs that are not everything has to be high end, not everything is leading edge. In fact, in certain applications such as analog ICs, it might be counterproductive to scale beyond a certain extent from a technology standpoint. You might have interference issues, device interference issues, and so on, which might prohibit you from scaling beyond a certain point. So it might even be undesirable for certain application sectors, and certainly certain standard ICs, commodity chips, low margin kind of chips, low end chips to manufacture on the latest fabs. So there's still going to be a substantial demand for 200 millimeter fab wafers. The investment in 200 millimeter fabs around the world, it is said to be inadequate. The demand for chips, if you look at it from 2015 to 2019, and even in the current global chip shortage, the demand for chips from 200 millimeter fabs, the older nodes, it does outstrip the supply. From a point of view of India, it can have several advantages, some of which I pointed out in starting with the 200 millimeter fab. Usually for an established chip maker who knows what they're doing, this is a mature, proven technology. As you have companies migrating their fabs to 300 millimeter fabs, you can have a lot of depreciated equipment in the market, which can be purchased. This will reduce the upfront capital investments that are required. If you are looking for foreign investors or investing partners, there is also a larger pool of companies, larger number of companies that know how to do these technologies. So you're choosing from a larger pool of partners, and there could be more interest in these technologies. Very simply, the mature technologies are simply easier to make them work from a yield standpoint, from a product quality standpoint, from simply running a commercial fab with these technologies perspective. Finally, as I mentioned earlier, running a commercial fab it involves more than just mastering the process technology. There are a lot of other factors, including planning, including having an ecosystem and so on, that go into running a fab efficiently. And also it would provide a lot of learning to lean on as India advances to more advanced technology. Generally, if you have a technology, you rely on previous technologies to get learnings from as you move on to the next technologies. It is very difficult to leapfrog technologies. Companies that have tried to do it, they've not always been successful. They try to leapfrog technologies and advance to the most to nodes in which they don't really have a lot of expertise. Now, whether a fab works out or not, India has had a number of non-starters. So whether a fab works out or not, the other opportunity that India, in my opinion, should certainly put some focus on is assembly and test, what I called out as OSAT. Like I mentioned earlier, this is where you obtain manufactured wafers. That is, these wafers have already gone through the front end of manufacturing. All the transistors are built, all the metallization is built. And then you dice up the individual chips, those individual squares that I showed on the diagram very early in my presentation. And then you bring them to a form where they can be mounted on a printed circuit board or a motherboard, as we call them. Generally speaking, this has a lower technology barrier. It has lower costs of investment compared to the front-end fab. And many countries, if you think about it, like Taiwan, South Korea, China, they first entered the semiconductor market through the space. In some ways, this is a logical backward integration from some of our current PCB assembly capabilities that we have. This is my final slide. I would like to conclude by presenting a SWOT analysis as I see it for the semiconductor industry in India. First, in terms of strength, India certainly has strong ambitions, particularly in the manufacturing of electronic systems, automobiles, and so on. Now, this is sure to translate to a growing demand by these end-use segments and a potential captive market if we choose to invest in the right technologies in India. Secondly, India has developed significant competence in IC design over the years. Thirdly, you have a very large pool of human capital. When I talk about human capital, I talk about two things here. One is the young people in India still want to study engineering. There is still an interest, which is not the case in every country in the world, particularly in the advanced countries. This is not really the case. So India has a vast pool of engineers who can certainly be trained to work in the semiconductor industry, similar to what has happened in the software industry. So when we started the software industry, it is not necessarily that we had a vast amount of talent in India, but the talent was trained to work in the software industry. It can involve partnerships with universities, initiatives taken by companies, and so on. The second, and perhaps an important human capital that I talk about, from my opinion, is the vast diaspora of very capable engineers and engineering managers at various levels who are actually residing outside of India, who are working in semiconductor manufacturing, who actually have a deep understanding of the technology and the dynamics and nuances of this industry. I don't talk about this lightly. Uh, and I don't talk about this in vacuum. If you look at countries like Taiwan and China, companies like Deloitte have done this analysis. They have certainly used this resource, this pool of resource to their advantage in developing their semiconductor industries. For example, if you look at who started TSMC and who led TSMC, it was an engineer, or it was an engineering manager who had spent 20 years in Texas Instruments. A number of early managers in TSMC were actually returnees who were trained in American companies. So this is certainly a large pool of resource that India should look at and see what it needs to do to capitalize on as it moves into the semiconductor industry. Finally, there is a recognition by the policymakers in India that there is a need to secure the electronic supply chain. I think this is a very good thought process, and it's very encouraging for the manufacturing of not just chips but other components as well, such as LCD displays and so on. In terms of weakness, I would like to call out a few. But one, India is certainly a late entrant into this market. If you look at countries like China, which are just coming of age in the last 2 years or so, really they've had commercial fabs. They have experience in running these fabs for a couple of decades or more. They have a trained workforce, so to speak. This also means that the technology that we are talking about now, it is fairly advanced. Even when I talk about a 28 nanometer technology, it's not a simple technology. So when companies move to 5 nanometer or 7 nanometer technology, it does not automatically mean that a 28 nanometer technology is easy by any measure or any stretch of imagination. Technology has become very nuanced, and India does not necessarily have the learning cycles needed to venture into these immediately. There could be concerns, real or perceived, about potential infrastructure weaknesses. Particularly, I called out power and water. I think I talked about in sufficient detail earlier about the importance of this to the semiconductor industry, to manufacturing. A third is the lack of an established support ecosystem. Now, usually a support ecosystem, if you look at a cluster of fabs, the support ecosystem around the fab, usually in the same geography, will be you will have equipment parts, you will have consumables, you will have makers of electronic chemicals, they will have some sort of presence in that geography. You will have companies that refurbish components, that reclaim wafers for you, and so on. Now, India does not have this kind of a support system, but to be fair, you cannot put the cart in front of the horse. This is something that has to be developed simultaneously. Third is the capital requirements and the ongoing capital requirements that's required. We have to see if we have an appetite for that. To be economically meaningful, I highlighted very early on that the IC manufacturing has to be done at high volumes to be meaningful. Modest scale fab, it has to manufacture somewhere between 30,000, 40,000 wafers per month for it to be meaningful. Then in terms of opportunities, the development of a fab manufacturing capability, it will be a long-term strategic investment from the point of view of securing the growth trajectory and the ambitions that India has in the remaining industries, particularly in the automotive electronics industries. It just makes logical sense to go there. It will create significant job opportunities. It will spawn secondary industries supporting the semiconductor manufacturing, the ecosystem industries that I talked about, and so on. In terms of threat, ensuring cost competitiveness and scale to stay competitive, particularly when you're investing in older nodes where your competitiveness comes with cost and scale. This will require continuous capital and R&D investments. We have to see if we have the appetite for that. Secondly, there are perceived inadequacies in infrastructure, policy stability, and so on in the general market, which could hamper our competitiveness. It could hamper our attractiveness to foreign investors, which is something that there is a little bit of onus on India to actually demonstrate that it is capable of operating commercial fabs on a meaningful scale. I will end my talk here with a final remark. Uh, this should not this kind of investment in semiconductor technology, we should not view it from a short-term perspective. It will not be a quick success, overnight success, similar to what we have seen in mobile assembly or mobile manufacturing. You have to view this from a strategic standpoint. The reason I say that is to bring a fab online. If I decide to construct a fab today, to make it operational and to bring it online and to achieve a meaningful device capability, yield capability, and to achieve a meaningful scale will take 2 to 3 years at the minimum, even on older nodes. If you want to develop a certain level of competence and dominance in this industry, we can look at anywhere between 10 and 15 years. If you want to develop a presence, if you want to really come of age in this industry. So necessarily you have to look at it from a strategic standpoint and not from a short-term gain standpoint. On the other side of this also kind of highlights the importance of why decisions and directions need to be set early on versus putting this off to later times if you really think that we are concerned about supply chain vulnerabilities and so on. Now, with this, I will actually turn it over to Mr. Venkatraman if you would like to make some comments.
Thank you, Dr. Nandini Venkatraman. You have given a wonderful talk. It was a very holistic, integrated talk on semiconductor industry. You have not left any aspect uncovered. And what is particularly impressive is, having talked about the global scenario, you have given a proper perspective and plans for the government of India to move on, suggesting that India need not copy the present pattern as in advanced countries, but it has to start with certain definite strategies like the type of chip size you should have and all this. I'm getting a lot of messages right now, and some of the people have said this is one of the best talks that I heard on the semiconductor industry in India in recent times. I congratulate you, Dr. Nandini Venkatraman, for this excellent performance. Mr. Swaminarayan Venkatraman, I request you to give a concluding remarks. And we have a few questions. Unfortunately, I'm not able to take it due to want of time, but Dr. Swaminarayan Venkatraman, I request you to give a concluding talk.
Thank you, Dr. Nandini. I mean, it was a wonderful presentation. I think all of us have a very, very holistic perspective of what the challenges for India are. If I can just summarize what we have listened to in the last 1.5 hours, I would say that, let's say, semiconductor is a strategically important industry for a large country like ours. And especially as we have become very heavily import dependent on vital semiconductor chips and other electronic components, especially from China and Hong Kong, which we know is a strategically very, very sensitive situation right now and likely to be in the future as well. And the value and volume of imports in this sector is only likely to keep increasing with the increased digitization that is going to inevitably happen in our country. However, unlike, I would say, oil, where also we have always been heavily dependent, import dependent, it's possible to reduce the dependency on chip imports by creating semiconductor manufacturing units within this country. I think we should not lose hope from your presentation. That's what I gather, that there are ways and means of getting into the global supply chain in semiconductor manufacturing, and that requires careful thought process. As Dr. Nandini has shown, semiconductor manufacturing requires huge investments, technology, and highly skilled manpower. And there are only a handful of companies globally that produce chips on a large scale, especially leading technologies, and none of them are in India. And not more than 8 or 9 countries have also successfully established wafer level manufacturing. So it's an extremely challenging situation for our country. And from what we understand, most of the new capacity which is going to come in the world is also likely to be in China. So that makes our import dependence all the more critically important. And it's also very clear from the experience of other countries that the government will have to come up with policies and lead to overcome these deficiencies. because especially where in countries where chip manufacturing has taken off, be it China, Taiwan, or South Korea, governments have been generous in putting the initial capital, apart from incentives like low interest rates or tax holidays and so on. And as you pointed out, the investments are not one-off. As the technologies evolve, the factories have to be updated, which means large investments every 4 or 5 years. So what global companies are looking for, as I would understand, is that they're looking for a long-term engagement from Indian government and Indian corporates. And if I may add to what Dr. Nandini mentioned, maybe announcing a policy for 3 to 5 years does not work. And global companies need a kind of assurance that we will have policy stability and incentives and such supporting structures which will be stable with a time period of 15 to 20 years in the future, and not only for 3 or 4 years which may change when another government comes into power and so on. So companies really need long-term policy stability and assurance of long-term engagement from our government in order to be assured of making investments in the country. Of course, there are, as you pointed out, there are issues of having secondary industry around fab units, companies that service, clean, refurbish, or provide other critical services. But this is like a chicken and egg situation. So I guess we will have to make a start somewhere. And especially in case there is a global crisis or some sort of a political isolation for India with respect to some of these major chip exporting countries, we become very, very critically vulnerable. So India has to be somewhat self-reliant. And if I were to conclude, the semiconductor chip is increasingly omnipresent in our lives, in every device that we consume. And this will truly test our resolve of becoming, like what Prime Minister Modi says, self-sufficient or Atmanirbhar. Thank you all for joining the webinar. And in case you would like to get in touch with us regarding this webinar or any questions you may have, you could send us an email or leave any comments behind the YouTube link, and we will try our best to get back to you as soon as possible. Thank you, Dr. Nandini. It has been an excellent presentation, and I'm sure everyone who's listened to this has been deeply enriched by what you had to share. Thank you very much. Thank you all for joining.
Thank you.